Hi, let's talk about the chi-squared statistic. It's a great tool to get started in cryptanalysis field. It's great for introductory SIGINT, and it's great to be able to differentiate whether you have garbage or whether you have usable text. And I can't tell you how many times I've had to scroll through 100 different examples to see which one made the most sense in a capture the flag. So what this is doing is this is alleviating a lot of the work that you have when you're decrypting different challenges within a capture the flag, trying to determine which one's English and which one's supposed to throw you off. So this is good for crypto. It's good for determining where you can find a cyber attack or where the vulnerability is, and it's pretty easy to code up. So let's go through it. Once again, I'd recommend Practical Cryptography. Great website. It's good for introductory learning. Doesn't talk about modern ciphers, but it talks about classical. So we'll use it for classical a lot. But as we're talking about AES, RSA, and post-quantum algorithms, this site doesn't cover it. It stopped working in 2012, but it's still relevant to get started in the industry for SIGINT and or practical cryptography. So once again, this is a tool to help alleviate a lot of work that you have when you're looking at capture the flag events, or you're looking at challenges associated with crypto or cryptanalysis. And essentially, the first line says it all. It's looking at two different distributions. The closer they are, the smaller the number. So if they're identical, they're 0. If they're further apart, then they're a larger number. And I wanted to harp on that the ciphertext, or the decrypted ciphertext, is looking at count, not probability, but the expected letter will be looking at probability. However, you have to differentiate early on what language you're looking at. So this becomes a problem when you're talking about poly substitution ciphers, and you're going to substitute English with another language like Spanish. However, you have to differentiate that early on, or else you're not going to get as accurate of results, because you're comparing distributions without the appropriate metrics associated with it. So for our example, pretty simple. We're using English, and I make sure everything's in lowercase so I can work with the ASCII2 value of 97 to 122. I create random garbage text so that I can compare it to the original text. And for this example, I use Wikipedia to get the letter frequency, since they're pretty standardized. I mean, they want everybody to have legitimate results, so in this case, there's no problem with getting it off of something like Wikipedia. However, you'll see later on in n-grams, or looking at bi, tri, or quad distributions, or character frequencies, I guess character set frequencies, that you can differentiate, you can create and differentiate letter frequencies based on any type of novel or text. I chose the first Harry Potter just because I'm a fan. So let's go back. So we're looking at Caesar text in this example. The original text, plain text, is defend the east wall of the castle. Most of this is for World War II. And here's the encrypted Caesar text. And what it does is it goes through the different distributions. So in this example, there's 18 A's that occur in this, and the expected frequency should be 0.082. In our example, it's 0.082. So what it does is it takes how many A's show up, subtracted by 162 times the letter frequency of A, which then will amount to 13.2, squares it, divides it by 13.28, and then you get your result. And what it does from here is you're supposed to add those letter sorry, the occurrence of each letter prop, propping up into the final result. So for this, for this example, it finds all the letter frequencies associated with the expected frequency, subtracts it from the count within the decrypted ciphertext, adds up all those different numbers to then get you your chi-square value. And if you look, remember the higher the number, the higher the chi-squared, the less likely those distributions are equal. And so we're looking at the lowest number here. Pretty simple, pretty straightforward. And what it's doing is it's able to differentiate a bunch of garbage from what the actual value is. And this will save you a ton of time in capture the flag and save you a ton of time with your cryptanalysis. That's actually the right answer. So let's go through inherent example I did. So I took the default English frequencies off of Wikipedia. I stored them in a dictionary for Python. And then all I did here was I printed off the dictionary keys. You gotta do the keys, then you do a length function, pass it to a length function, pass it to a string so you can print it in this print function. And I did a simple for loop here, enumerating over each letter and frequency within the default English dictionary frequency, English dictionary frequency. And from here, I just printed out what the probability occurs with each letter. However, I did make a mistake. And I did not format this over here so that they're all standardized. But I think it's pretty intuitive at that point. So here's the meat of it. I created a chi-squared function to take in whatever decrypted ciphertext you have. For the standard, I just put cryptanalysis. And then I used the alphabet, and in this scenario, I just used the lowercase ASCII2 values for English, which is 97 to 122. Then I use the expected frequencies associated with each ASCII2 value that's in the range of interest. Here's where the programming gets a little more difficult. So I created an expected frequency mapping, a ciphertext frequency mapping, and then a cipher chi-squared mapping or dictionary. And so don't get confused on frequency mapping, because this is really just a count mapping, and this is a frequency mapping. I could always change it. It was just easier for me at the time. And then what happens is I run through each, so I enumerate through the set of letters associated with the decrypted ciphertext. So remember, a set only has one occurrence of each letter that happens or occurs within that text. And I then take the count minus the expected frequency associated with a letter for the length of that decrypted ciphertext. I square it and then divide it by the expected occurrence of that letter within the length of the ciphertext. Here I printed out the example to show you that it's representative of what page we were on previously. Once again, shows a lower letter. Now, the actual result is going to be slightly varied from what you see on the other page, only because we used a different frequency list associated with our analysis. Now, if we were to use the same frequency probabilities, then it would be the same result, but it's varied to such a slight degree that it doesn't cause a problem. Now, getting the right frequencies is probably one of the hardest things and easiest things. But if you are using wrong frequency mappings, like, so for example, if you're using English when you should be using Spanish, then you're going to get the wrong result. And so sometimes you have to run over multiple page tables, and that's what a page table is really just the think of it as the ASCII values associated with a particular language. And so you got to make sure you have the right page tables. And so from this example, we go further. I create a bunch of random text so that you can see more examples. So I just use the rand int function within Python to generate a whole bunch of random characters within the ASCII2 range of 97 to 122. And I create 15 different decrypted ciphertext texts. So these are really just garbage, random values and variables. Going further, I give you a legitimate text. I say, hello there, we are starting this section on statistics to make everyone aware of the struggles and difficulties of cryptanalysis, as well as the tools. Enjoy this lab. I use a list comprehension to join the letters together to create lower cases in case because there's capitals, and only take the letters that are ASCII2 values within our range. So is alpha is checking if it's part of the alphabet. So I then map all the text, so 16 different texts, to its chi-squared value and store it in a dictionary, and then eventually create kind of what we saw before on the other page, and we go down the decrypted ciphertext, and we go down the chi-squared values associated with that decrypted ciphertext, and we see that we actually do get the value that we're looking for at the end. So we get 20, which is the lowest, which means it's most identical to the regular English alphabet. And it's hello there, we are starting this section. And that's how you do a simple chi-squared associated with cryptanalysis. So there's more resources and tools and techniques on SigCryptL. I look forward to working with you guys, and I'm excited to get this started. It's been a long time in the making, and I'm finally ready to start doing some competitive SIGINT. So you guys have a great day.